Hello everybody. As first module of our course, let us study logic and its application to computer science. Basically logic, mathematical logic is a tool which works with elaborate compound statements. What I mean by a tool is, it is a formal language for expressing complicated compound statements. You can express complex, complicated statements using this formal logic, and you can reason or infer what is this particular complicated compound statement is saying. It is a truth statement or is a false statement, kind of inferences you will be able to make via this tool called mathematical logic. And another important thing is, it deals with different methodologies of proving a statement. What I mean here is, you got a statement like Pythagoras theorem, like a statement about the right angle triangle. Some of the lengths of sides of a right angle triangle, some of the squares of sides of a right angle triangle is equal to square of the hypotenuse. This is a statement. You need to prove that. Pythagoras is the guy who has proved it. To prove any statement or to disprove any statement for that matter, logic provides different methodologies how you can prove a statement or disprove a statement. This subject is dealt with basically how to express a complicated compound statement and how probably you can reason about it, you can infer about the complicated statements, compound statements, and methodologies of proof. Before getting further in this subject in logic, basically we study propositional logic. We will see the basic definitions of propositional logic. We will see what a proposition is, how a multiple propositions can be put together to come up with a compound statement, and how you can reason about it, and how you can say two compound statements are equivalent. And then we get on to predicate logic, which is slightly generic version of the propositional logic. That is the agenda of this module. Propositional logic, historically this is being discovered or originated from Aristotle in 300 BC. Afterwards it has been worked by Soli for some time, but however the logic that you and me are seeing, the Boole is the one who is responsible for formally writing this logic and the reason for it to be the shape where it is today. Afterwards a lot of people worked and bettered it, but it is the Boole who formalized it. Before getting into what propositional logic and all, first let me define what a proposition is. A proposition is a simple declarative statement with some definitive meaning. There should not be any ambiguity or vagueness in that declarative statement, and that statement should be either true or false, but it should not be both, or it should not be anywhere in between true and false. Such a statement, such a declarative statement is called a proposition. Simple proposition is nothing but declarative statement whose truth value is either true or false. You should be able to say whether the statement is true or false at a given point of time, provided you are given all the data about the statement. That is what a proposition is. So to understand it better, let us look at some of the examples. First example I take is, it is raining in a given context. In a given context, at this point of time, you should be able to say whether it is raining or not. Whether the truth value is either true or false. I will be able to say this statement is true or false in a given situation. and there is no vagueness about it, and it is a declarative statement, hence I call it a preposition. Beijing is the capital of China. This is very much a declarative statement, and truth value of this statement happens to be true, hence this is a preposition. It doesn't mean that truthness of a statement is false. It doesn't mean that that particular sentence is not a preposition. For example, if I say Mumbai is capital of India, this is a declarative statement. There is no vagueness in it. Of course, the truthness of this statement is false. Still, Mumbai is capital of India is a preposition for us. So preposition is nothing but a declarative statement which has got its truth value as true or false. Another example is 1 plus 2 is equal to 3. This is definitely a declarative statement and its value happens to be 3. However, it is a preposition. We see some of the things which are not really prepositions. Who is there? This is basically an interrogative questioning statement. So this cannot be a preposition. And in some meaningless interjunctions like la la la, ho ho ho, all these things will not be prepositions. Just do it, an imperative statement, command, these cannot afford to be prepositions. A vague statements like yeah, I sort of doing it. And another expressions, 1 plus 2, it is just an expression, it's not a sentence. So they cannot be prepositions. Now, I hope we understand what a preposition is. A preposition is a simple declarative statement whose truth value is either true or false, but not both. Another thing that we deal with is operators or connectives. If you take natural number system, you take any natural numbers, there are a lot of operators that you are already aware of that are working on set of natural numbers, isn't it? You give me any two natural numbers, I have got an operator that is called plus addition that will be operated on these two operands, two natural numbers, and then you get a result out of it. Hence, an operator basically combines one or two operand expressions into a larger expression. If you give me two natural numbers, say 7 and 9, and then I apply this addition operator on 7 and 9, the resultant expression that I get is 16. This is what an operator takes some operands and operates upon it and gets a result out of it. This is what an operator is. So we all know lot of operators that have been working on set of natural numbers, real numbers, rational numbers. Hence a lot of operators we already know it. But now what we talk here in this course is the operators that are operating on prepositions. That is what we deal with now. Having known what a preposition is, you will have a number of prepositions. The point that we are discussing is what are the operators probably that I can apply on these prepositions to get a compound statement. That is what we are talking. Hence, the preposition logic is the logic of compound statements built from simpler statements using so-called Boolean connectives. The operators that will be operated on these prepositions are called Boolean connectives. Appropriately, they are called Boolean connectivities because each preposition basically is having a truth value or false value, equivalently having a value of 1 or 0. A preposition, it is raining, it is either truth or false. Equivalently, you can say that it is either 1 or 0 if you represent truth as 1 and false as 0. Because you are all dealing with prepositions, and prepositions always assume values either 0 or 1, the operators that are being operated on them are called Boolean connectives or Boolean operators. The name is so nicely put there. Because they are operating on Boolean values, they are called Boolean connectives. Okay. If you would like to know what are the applications that this preposition logic has got in computer science, there are lots of applications. You can whatever the conditions that you are putting in your programs are because of this propositional logic, and whatever the queries that write into database are in terms of prepositions only you are trying to write there, and you are trying to conclude or infer something from a compound statement, and all digital electronic circuits uses this propositional logic to a large extent. So, having known what a preposition is and what are the operators that are, and having known what a operator is, we will see some of the operators that will be operating on these prepositions. Basically, we study following operators called negation operator, that is not operator, conjunction operator, that is and operator, disjunction operator, that is or operator, exclusive or operator, that is XOR operator, implication operator, and biconditional operator. For any operator, if you realize there is something called RET, order of operands that it will be operating upon. Okay. If you see the addition operator, the plus operator that is acting upon natural numbers, how many operands, how many operands that it will be working on? 2. When I say 7 is added to 8, I say 7 plus 2, that means plus operator is taking 2 operands into consideration. Hence it is called a binary operator. It needs 2 operands to be operated upon. Hence the addition operator on set of natural numbers is a binary operator because it needs 2 operands. Similarly, there are operators which takes 2 operands, which takes 3 operands, which takes 1 operand. Here we deal with operators of RET, unary, binary, trinary and all. For example, negation operator that we are going to speak now is a unary operator. What do I mean by this? Unary operator takes only 1 operand and it acts upon it and it gets a result out of it. For example, the unary operator transforms a preposition into its logical negation. What I mean here is, if I have got a preposition and I apply this negation operator on this preposition, I get a negation of the preposition that I am talking of. For example, I have got a preposition called P called I have a Honda City car. This is a preposition. Nobody can deny it because it is declarative statement which is having truth or false value, and I am having really Honda City car, hence its truth value is true. Now when I put negation operator on top of this preposition, I will get a result like I don't have a Honda City car. This is what exactly means by negation operator. When on any preposition, if negation operator is acting upon, you get the reverse meaning or the opposite truth value of that particular preposition. And the one way to better understand it is, the operator is defined this way. Okay, whenever actual preposition P is taking true as its value, then this negation operator is defined that negation of P will take false as its value. When actual preposition is taking false as its value, the negation of preposition is going to take truth as its value. This is how it is defined. Better remember this. What I am trying to say is, like binary operator, like operator like addition plus operates basically upon two natural numbers called 7, 8 to give you the output, that is 15. This is called a binary operator because basically it is acting upon two operands. Similarly, we have got unary operators on on set of integers. How does it work? It takes only one operand, say 8, and when this particular thing is being operated on plus 8, what you get is minus 8, and you got say minus unary operator when it is operating on say minus 12, what you get is 12. Thus you got binary operators, unary operators are natural numbers. Similarly, we will have binary and unary operators on the set of prepositions also. We will see one negation operator, one unary operator, that is called negation operator. How it works is, it transforms a preposition into its logical negation. How it works is, this negation operator basically transforms a preposition into its logical negation. What I mean by that is, if I have got a preposition called P called I have a Honda City car, when this unary operator called negation operator is acting upon this preposition P, then what the result I get is, I don't have a Honda City car. Okay, but you need to understand it basically from truth table how this operation is basically defined on. Given any preposition, the preposition that we are considering, like I have a Honda City car, absolutely there is no problem in accepting this as a preposition because it is a declarative sentence which is having a definite meaning and which is having its truth value as true or false. Because I am having already a Honda City car, its truth value happens to be true. Now the point is, when it in this case it is true, in other case it may be false. So this operator basically defines when my preposition takes truth value, what is the truth value after this operator being applied upon. This operator defines it. When my preposition takes truth value, when this operator is acting upon that preposition, the result I get, the resultant preposition will have its truth value false. Similarly, when my preposition's truth value is false, when this operator is acting upon it, then the resultant preposition will have its truth value as true. This is being defined. This is how this negation operator is defined. Intuitively it is correct. I just want the negation of the preposition, so the truth value should get reversed. So this is what is the negation operator. Then we will see another operator, and this is a binary operator. That means it needs two operands for it to be acted upon to get the resultant value. This is called conjunction operator. It combines two prepositions to form their logical conjunction. Okay, and if you are wondering how this particular symbol has come, if you are wondering about it, maybe one of the guesses is, this is basically an AND operator, and you write typically AND like this, and A may you just delete this particular vertical line, then you get this particular operator, particular symbol. Maybe that is a wild guess how this AND is being represented by this particular symbol. However, we will see how this works. If I have got two prepositions like P which is nothing but, which is defined as I will have a salad for lunch, and Q, there is another preposition called I will have a steak for dinner, which is represented by Q. These are prepositions. Absolutely there is no misunderstanding over here, because these two are very much a declarative sentences whose truth value is either true or false. Then this operator, this conjunction operator, is defined as P and Q will be read as I will have salad for lunch and I will have steak for dinner. This is how it is defined. Okay, as far as English goes, it just combines the two values by conjunction operator, by and. We will see the truth table, and we will see whenever P is, when P and Q assumes different values, different truth values, how this particular conjunction operator is defined. This is defined, there is, just try to get it, okay, there is this is defined like this. With an intuition it is defined, we will see the intuition afterwards, but this is defined. When P assumes false and Q assumes false, P and Q is defined as false. When P is false and Q is true, P and Q is defined as false. This is how it is defined. When P is true and Q is false, P and Q is defined as false. When both of them are true, P and Q are true, then P and Q happens to be true. This is how it is defined. What is the intuition behind it? When somebody says that, when somebody comes and tells me that, sir, I have got a compound preposition with me, something like I will have a salad for lunch and I will have a steak for dinner. This is definitely a compound statement because it has got two prepositions connected by the binary operator called and. This is a compound statement. If somebody comes and tells me that this compound statement is true, then I can always conclude that I will have salad for lunch and I will have salad for dinner. If somebody says that the compound statement of P and Q, I will have a salad for lunch and I will have a steak for dinner, is false, then probably you have only, I'll have only steak for dinner and I will not have I will not have salad for lunch, or vice versa, or both prepositions can be false. This is what I can make out. This is what is quite natural also. When somebody says that the statement of I am having Honda City car and I am having Tata Indica, if the statement is false, then he can have only one or he cannot have both. That is what it means. The same way it has been defined, same way this even the resultant value of the compound statement is defined. When P assumes false and Q assumes false, P and Q assumes is defined to be false. This is how it is defined. The intuition behind this is quite from natural language that we speak. If any of the preposition is true and the other preposition is not true, the resultant compound statement that we get has to be false. The compound statements will be true only if both the prepositions are true. This is how in natural language we use it. The same way this has been defined over here. We will see another binary operator. It also takes, it is binary, hence it takes only two operands here, and it is OR. The way we generally speak OR is the same way it has been defined even here. If I got two prepositions called P and Q, P is my car has a bad engine and Q is my car has a bad carburetor. P or Q is defined as either of the two statements, either my car has a bad engine or my car has a bad carburetor. This is defined, the syntactical semantical meaning of this is either this or that. However, the truth table for this OR is defined like this. because you have got 2 operands, you are going to have 4 rows in your truth table. This is basically called a truth table. Probably this is called truth table. Why? Because P and Q, when you are operating on P and Q, the maximum number of values, combinations that you get out of this, basically when P can take only true or false and Q can take only true or false, and they are independent, only 4 rows you are going to get. Hence, any binary operator that is operating on 2 operands will have to define for these 4 combinations, isn't it? Because P can take either true or false, Q can take either true or false. So how many combinations you will get? This is typically a 9th class problem. P can take only true or false, and Q can take true or false, and they are independent in nature. Then how many combinations you will get is 4 combinations. For all these 4 combinations, you need to define the values of this particular operator when it is acting upon these 2 operands. So it is defined like this: when P assumes false and Q assumes false, P or Q will be defined as the false. Similarly, when P takes true and Q takes true, then P or Q takes true. This is how it is defined. So it is quite intuitive. In real life also we will do that. When I say make a statement called either my car has a bad engine or my car has a bad carburetor, for sure my car has bad carburetor engine might have been true, otherwise my car has a bad carburetor has been true, otherwise both have been true. Only this is a situation where I can make this statement. So similarly the values in the truth table have been defined. This operator is also called inclusive OR. Why? Because it includes the possibility of both P and Q are true. What I mean here is, if P and Q, even if both of them are true, I am defining P or Q as true. So this is what I am saying, that it includes the possibility of both P and Q being together true at the same point of time. Even if both of them are true, I define P or Q to be true. Of course, if one of them true, I have to define P or Q is true. That is there anyway. But even if both of them are true also, I am defining P or Q to be true. This is inclusive of this particular condition. Hence, it is called inclusive OR. You will get better understanding when I go to exclusive OR. Then you will appreciate the difference. Right now, you just understand how this particular operator is being defined on these 2 operands. We will take an example before going further, and before going further we will take an example, and before that we will see whether these operators are commutative or an associative. What do you mean by commutative? I say addition operator is commutative. Why? Because 7 plus 8 is always equal to 8 plus 7. It hardly matters whether you operate on 7 and 8 and 8 and 7. The result is the same. Hence, the addition operator is commutative. Similarly, you just look at it. Subtraction operator is not commutative. Okay, and now we will see the operators that we have defined, binary operators, like I have got 2 prepositions P and Q, and I have got an operator called P and Q. Is it commutative? Certainly, because P and Q value will be always same as Q and P. Hence, the operator and operator is commutative. When I say we'll go to our example and see, we go to our example and see when we got a statement like I'll have salad for lunch as the one statement and I'll have a steak for dinner as another statement, then I will have a salad for lunch and I'll have a steak for dinner is having the same meaning as I will have a steak for dinner and I will have a salad for lunch. The meaning will not change. So P and Q and P will always be the same. It doesn't matter what you put first and what you put second. Hence the addition, the AND operator is commutative. And similarly associative. I mean, when I got 7 plus 8 plus 10 will be always equal to 7 plus 8 plus 10, isn't it? You are able to do this simply because natural numbers under the operator addition satisfies associative property, associative law. You are able to say because of that. And now even the same holds good even for prepositions. If you have got a 3 prepositions called P, Q, R, and then you consider this P and Q and R will be same as P and Q and R. Basically the meaning will not change. Meaning will not change. They remain the same. Hence they also satisfy associative property like addition. So both your AND operator and OR operator satisfies both commutative and associative laws. Now we will see how we represent this particular compound statement, English compound statement. Generally these prepositions will be represented by small letters, not by capital letters. If you have got a preposition called, simply preposition called, I just saw my old friend, is it a preposition or not? Definitely it is a preposition. It is having its truth value as true or false. It can be false as well. And it is very much a declarative statement without any vagueness in it. Hence it is a preposition. Generally a preposition kind like this will be represented by small letters. You can choose any letter. For example, I am choosing F as F to represent this particular preposition. Then I have got another preposition over here. He is grown. This is another preposition and I represent this preposition by G. And there is another preposition, I have shrunk. I represent this probably by S. Now the point is, if I have got a compound English statement like this and I would like to represent it in preposition logic with the symbols, then how do you do it? This is the way to do it. F and G or S. It means that I just saw my old friend and either he is grown or I have shrunk. This is how to represent it. Given an English statement, try to see what are the declarative sentences, declarative statements there. If only declarative statements there, you can represent it in propositional logic, otherwise you will not. If your compound English statement that you have got with you is so nice that all its constituent simple statements are declarative without any vagueness, then you represent it by some symbols, then you will be able to connect them with the operators that we are talking of. For example, this thing definitely we can represent it like F and G or S. This is how we can represent. Here you have to be very careful when you are putting parenthesis. This is a correct way of doing it because it is exactly matching with the what is given to us in English. If you have written this way, F and G or S, it means that I just saw my old friend and he is grown or I have shrunk. But what is told for us is not that. What is given to us is, I just saw my old friend, and then the other statement is coming. Hence you have to put parenthesis here, not here. With your English statement you have to understand it, and you have to carefully transform it to prepositional logic and put your parenthesis carefully. Otherwise it is going to be chaos. And if you don't put any brackets, it is ambiguous, isn't it? What does it mean? I just saw my old friend and he is grown, or I have shrunk. Does it make any sense? Where is and, where is or? In English you have got a beautiful things like comma and all these things you have got. To represent it, you have to put your parenthesis carefully, otherwise it is going to be a really mess. And however, there is some precedence. When you don't put such brackets, the precedence comes into act, and it will take its own action. For example, not operator always takes precedence over and or. What I mean is, if I have got a compound statement like this, not S and F, it definitely, though you don't put brackets, it means that if this is a valid statement and somebody comes to me and says that not S and F, and I don't have any brackets, what I get to assume, what I get to understand is bracket is here, not anywhere, not here. You are getting what I am saying? This is what I mean by precedence. Okay, when and operator, not operator is there, soon after that there is a preposition, then you understand that this not operator is only for this preposition, not for this compound statement. That is what is precedence. We will do a simple exercise. Given simple prepositions and some operators, and we make a compound statement. It is purely in prepositional logic, and we will see what is the English meaning of it. We have got three prepositions, P, Q and R, where P is it rained last night, Q is the sprinklers came on last night, and R is the lawn was wet this morning. If you have got these three prepositions and say not unary operator, not is acting upon the preposition P, not P. What does not P means? What does not P tell us? It tells us that it did not rain last night. And what is this binary operator and, when it is acting upon R and not P? What does this guy says? This guy says the lawn was wet this morning and it did not rain last night. This is what the meaning that it indicates us. And what does this sentence mean? Not R, or P or Q. When you are given these prepositions, it means that either the lawn was not wet this morning, or it rained last night, or the sprinklers came on last night. This is what it means. So given prepositions and make a compound statement out of it, and we will be able to probably say the English equivalents of that particular compound statement. We will see another binary operator, and that is called exclusive OR operator. It combines two prepositions to form their exclusive OR. It is, you may call it an exjunction, because other is conjunction. You can call it exjunction because it excludes the things. Let us see what do we mean by it excludes some things. Suppose you have got two prepositions called P and Q, where P is I will earn A in this course, Q is I will drop this course. Then exclusive operator called the exclusive OR operator this guy is defined, he is meant like I will either earn A in this course or I will drop it, but not both. I don't do both. Either this or that, but not both. What is conjunction? What is the OR operators telling? If I say P or Q, it means that when somebody comes and says that P or Q, this compound statement is true, then what I get to understand is either I will earn an A in this course, or I will drop this course, or I will earn A in this course and I will drop this course, both. So, the three possibilities that I can think of when somebody comes and tells me that P or Q, this compound statement is true, these three things they can infer from. However, but this guy, this exclusive operator, when somebody comes and tells me that P or Q, this compound statement is true, then I can always say that I will earn A in this course or I will drop this course. There is no other inferences that I can make when I know that P exclusive Q is true. This is what the difference. Here it excludes the possibility of both prepositions being true, whereas usual OR, it includes the possibility of both being true. That is why it is called inclusive OR and this is called exclusive OR. It excludes the possibility of both being true. That is why it is called exclusive OR and it is called XOR. However, because it is a binary operator acting upon two operands, we have to define, and this operator defines for each combination the resultant truth value. When P and Q happens to be false and false, then P exclusive OR is defined as false. When P and Q happens to be false and true, this is defined as true. Either of them is true, this is defined as true. Look at this. When both of them are again true, P exclusive OR is defined as false. In inclusive OR case, it is defined as true. That is how the difference is. It excludes this possibility. And here, I mean, we will have some difference with natural language. Basically, to conclude something from an OR statement in natural language, we will take context or situation into the consideration to see whether both being true is a case or not. For example, if somebody comes to me and say that the statement like the compound statement like Pat is a singer or Pat is a writer, if this statement is true, if somebody comes and tells me, then what I get to understand is three things I understand. Pat is a singer, or Pat is a writer, or Pat is a singer and Pat is a writer. These three things can be true when somebody comes and says that the compound statement is true. There are three possibilities that I can make out. But somebody comes and says that Pat is a man or Pat is a woman, then I will have only two possibilities. What are they? Pat is a man or Pat is a woman. He cannot be both. This I don't consider. So basically, natural language OR is being a little bit loosely used. You take into consideration the situation, context and all to see whether both being true is a case or not. Like in this case, Pat is a man or Pat is a woman. If somebody comes and says me that this statement is true, I get to understand only two things, not three things. What are they? Pat is a man or Pat is a woman. The third possibility will not exist because of the context. In the earlier context, like Pat is a singer or Pat is a writer, considering the situation, context and all, I will have three possibilities. Pat is a singer or Pat is a writer, or Pat can be both. So this ambiguity is being broken in propositional logic. We have got exclusive OR operator and we have got inclusive OR operator. We use as and when it is used, as and when it has to be used. We don't use one for the other. as in English. We will see another very important operator, binary operator again, that is called implication operator. This is the implication operator is P implies Q. Basically it states that P implies Q. So there is a lot of scope for people to get confused over here. If you have got two prepositions, we will understand it slowly. We have two prepositions called P, you study hard, and another preposition called Q, you will get a good grade. Then P implies Q. In English it means that if you study hard, then you will get a good grade. That is what the English meaning of it. It does not say anything. Okay. And like when operator is defined, you have to define the resultant value when depending on what the operand we have to define the truth value of the resultant depending on the truth value of the operands, that is P and Q. For each combination of P and Q, you have to define the truth value of the resultant. Here it is defined like this: when P assumes false and Q assumes false, then P implies Q is defined as true. When P assumes false and Q assumes true, then P implies Q is defined as true. This is how it is defined. So if you see it, the only false case for this particular operator, for this operator, this is the truth value of the result is when P assumes true and Q assumes false, then only this compound statement called P implies Q will be false. In all other cases, irrespective of P and Q values, this statement takes truth value. Are you getting what I am saying? It is the way it has been defined is implication operator. For all other combinations, it is going to be true. Only one combination it is going to be false. That combination is when P happens to be true and Q happens to be false. Only in that case P implies Q assumes false. Yeah, why I am saying it is little bit tricky here. Generally people assume that when I have got a statement called P implies Q, then people get to understand that P causes Q. That does not mean that. P implies Q is a compound statement. When can I assume Q is true? Only under situation, only in this situation. What is that situation? I know that my preposition P is true and I know the statement is true, P implies Q, then I can say Q is true. That is only it is saying when P implies Q is true, and I also know that P is Q, then I can conclude Q is true. Otherwise I will not be able to say anything about Q. Depending on the values of P, I will not be able to judge the truth value of Q. Okay, we will see another nice example. You tell me this particular statement, first of all, this statement 1 is equal to 0 implies pigs can fly. Is it a compound statement? Yes, very much. This is a compound statement because this is very much a preposition like small p. I can represent it by small p. Is it a preposition? Yes, very much. There is another preposition called Q. And fortunately here, now this is the compound statement that we are talking. This is the compound statement that we are interested in now, isn't it? Now here we would like to know what is the truth value of this particular statement. The truth value of this statement is true or false, that is what we are interested in. Then what is the truth value of P? What do you think the truth value of P can be? 1 is equal to 0, it is a meaningful sentence without any ambiguity and it is having truth value as false, isn't it? Its truth value is false. Pigs can fly. What is it? It's a meaningful sentence, okay, but its truth value happens to be false, we all know it. I hope there is no confusion over here. Now to know whether this compound statement is a truth statement or a false statement, I aptly go to my truth table and see when my P happens to be false, and my Q happens to be false, then what is my truth value of P implies Q? It is true. Hence I say this statement is true statement. You are getting what I am saying? How we will decide it? This is how we are going to decide it. We have got a complex statement, it is having couple of prepositions there and the operator is implies. With the compound statement that we have got is 1 equal to 0 implies pig can fly. Then you have got two prepositions and one preposition called 1 is equal to 0 is assuming the value of false, we all know it, there is no confusion. Pigs can fly is another preposition which assumes the value of false, there is no confusion about it. Now we would like to know the truth value of the resultant statement. We aptly go to the truth table, we will see for truth value of when P happens to be F and Q happens to be F, what is the value of P implies Q? It is true, hence this compound statement is having truth value as true. That is how we do it. We will take couple of more examples to get it very clear, because this is where there is a possibility that people can get wrong. We will see this particular compound statement. If Tuesday is a day of the week, then I am a penguin. This is a compound statement because there are two prepositions nicely connected by a connector or operator. What are the two prepositions? Tuesday is a day of the week. This is one preposition. This is one preposition, and there is another preposition called I am a penguin. This is another preposition. I have got two prepositions. What is the operator that is acting upon these two prepositions? Implies. It basically says that T implies P. That is what it is trying to say. Now we would like to know the truth value of this compound statement. Like we have done in the earlier example, what we do is, what is the truth value of the preposition T? Tuesday is a day of the week. It is having truth value as true or false? Definitely. Tuesday is a day of the week, hence it is taking truth T as its truth value. I am a penguin, definitely I am not, hence it is having truth value as false. Now to know whether the statement is having truth value true or false, what I go is, I go to this particular combination. When T happens to be true and Q happens to be false, then P implies Q happens to be false, hence this whole statement happens to be false, because the first preposition is having true as its truth value and the second preposition is having false as its value. When you have got first preposition as the truth and second preposition as the false, you get the resultant truth value as false. And for all technical notation and purposes and all, whenever you got thing like this, P implies Q, we call P as antecedent and Q as consequent. Here what is, so whenever antecedent is true and consequent is false, that is in fact the only case when P implies Q can be false. In all other cases P implies Q will be true. This is how it is defined. Okay, we will see another example. If 1 plus 1 is equal to 6, then Anna Hazare is president. It is true or false? Yeah, we will see that 1 plus 1 is equal to 6. There is no problem when we call it a preposition, and it is assuming the value of false, and Anna Hazare is president, at least as of today, as of now he is not, so it is a false statement. When antecedent assumes false, consequent also assumes false, then P implies Q, the implication operator, when operated on these two operators, the resultant value will assume the truth value as true, hence this statement is going to be true. You get what I am saying? Because antecedent is taking false value, consequent is taking false value, I aptly come here. When both of them are taking false values, then P implies Q takes truth value. That is how implication operator is defined. Hence this statement is a truth statement, or is having a truth value as true. Take another example. If the moon is made of green cheese, then I am richer than Bill Gates. Because both are false, then we can definitely conclude it is true. The resultant statement is true. That is how we have to say how a compound statement can be true or false based on the values that the antecedent and consequent assumes. However, P implies Q has got different ways how people call it. People call it P implies Q, some people call it if P then Q, some people call if P Q, when P Q. All these are equivalent and they mean the same thing, that is P implies Q. And given a compound statement like P implies Q, let us see what is its converse, inverse, contrapositive. This is generally we use it, isn't it? Given any statement, what is the converse of this statement, what is the inverse of this statement, what is its contrapositive, all these things we do talk. So for a given statement P implies Q, compound statement P implies Q, the converse is Q implies P, its inverse is not P implies not Q, and its contrapositive is not Q implies not P. This is how the notation is. Converse is Q implies P, this is quite intuitive. Inverse is not P implies not Q. Its contrapositive is not Q implies not positive, not P. So now, given, I mean in English also it is quite natural, I make two different statements, okay, but the meaning can be the same, isn't it? I can make two sentences, but actual meaning or inference of the two statements can be the same. Here you are seeing 4 compound statements, okay, but they can be same. How do you examine whether two compound statements, like in English I can take two things, the context is the same. So just because two sentences, there are two different statements, doesn't mean that they really mean two different things. Here you have got 4 compound statements. Are they really different, or any two of them is the same? that is true even going forward also. You got really compound statements. Now you know how to make a compound statement, isn't it? If you got a P, Q, R, S, T, then you can make a number of compound statements, P not Q, R, S, R, T, not T, and all these compound statements you can make. You can make a number of compound statements like this. Making so many compound statements does not mean that really they mean different. Some of the compound statements can be the same. How do we check it out? Okay, so we will figure out which of the two compound statements are really the same. So there is a way to do it. How generally people do it is, in fact we will show that of the four statements that we have got, P implies Q is same as not Q implies not P. These two statements seemingly different, but they mean the same. Their truth value happens to be the same precisely. P implies Q truth value and not Q implies not P's truth value is exactly the same for any combination of P and Q. What I mean by here is, when you have got two operands like P and Q, whatever the value that P assumes, what are the truth values that it can assume? It can assume true or false, and Q can assume true or false, and you got how many combinations like that? You got four combinations like we have been seeing like this. P can assume false and Q can assume false, P can assume false and Q can assume true. There are only four combinations that you can think of. For all these combinations, the P implies Q, truth value of P implies Q and truth value of Q implies P, if they are the same, then we say that these two are the same, are equivalent. Otherwise, the columns over here should be the same. Whatever the value here, you should have the same value. Whatever the value here, you should have the same value. Whatever the value. If these two columns are same, then you can confidently say that though they are seemingly different, but they don't mean they mean the same. That means they have got the same truth value for different combinations of P and Q values. So this is quite easy, because P, Q, if it is assuming false and false, we know that P implies Q takes truth as its value. When P assumes the value false and Q assumes false, P implies Q takes false value. This is how it is defined. When P assumes a false and Q assumes true, then it takes false, then it takes false, then it takes true. In fact, we have seen that the only one way that P implies Q can take false is when P takes true and Q takes false. That is the only combination where P implies Q is false. In all other combinations it is true. Hence we get this. There is no problem in getting this per column up. Then given P and given Q, you know how to compute not Q, isn't it? Given F as Q's value, what is not Q? It is true. If it is Q is true, then not Q is false. When Q is false, not Q is true. When Q is true, not Q is false. Similarly, you can compute the values of not Q and not P. And now you see here, when not Q implies not P will be false, in only one case it will be false. That case is when not Q is true and not P is false. Only in this case the P implies not Q implies not P will be false. In all other cases it is true. So you can confidently put true over here. If you see, these two columns are exactly the same. What does it mean? For whatever the values that it takes, P and P implies Q and not Q implies not P takes the same truth value, hence they mean the same thing. That is how we prove equivalence of two compound statements. We will see one more biconditional operator that is P if and only if Q. P if and only if Q states that P is true if and only if Q is true. That is what it means. We will take two prepositions. Congress wins 2014 elections. Rahul will be Prime Minister for all of us in 2014. These two are prepositions. Depending on situation, depending on the context, the values may vary. Then P if and only if Q means if and only if Congress wins 2014 elections, Rahul will be president for all of us in 2014. That is what it means. So let us see how the truth values of the resultant is defined. Truth values of the resultant that we got when if and only if operator is operated on two prepositions called P and Q. These two are operands and the operator that we are talking is if and only if. It is defined like this. Okay, when P assumes false and Q assumes false, P if and only if Q assumes will take truth value, will take true as its truth value. It is defined like that. When P assumes false and Q assumes true, then P if and only if Q, this compound statement will take false as its truth value. When P takes truth and Q takes false, then P if and only if Q takes false, and when P takes true and Q takes true, P if and only if Q takes truth as its truth value. This is how it is defined. And similarly, when we say that P implies Q, when we talk, we said that it does not mean that P is true or Q is true, or it does not mean that Q is true, or it does not mean that P causes Q. It does not mean that. In certain situations, if we know truth value of P and we know the truth value of P implies Q, then I can conclude about the truth value of Q. That too is known in one case. In other cases, we can't even conclude that. Similarly, here P if and only if Q, if and only if Q does not imply that P and Q are true, or that either of them causes the other, it does not cause the other, or that they have got a common cause. It is not that. Okay. When I know that P if and only if Q, this compound statement is true, and then when I somehow know that P is true, then I can confidently conclude that my Q is true. Otherwise I can't do it. I can't say that. If I know the truth value of compound statement and another preposition, then I will be able to comment on the other, but otherwise not. So successfully we have seen one unary operator, that is not, and 5 binary operators, that is and, or, exclusive, or, implication, and if and only if. Okay, these are the operations. Now we have seen what a preposition is and what are the operators that are operating on these prepositions, and by applying them suitably we can come up with compound statements. And equivalently, in prepositional logic we call not as and as this, or, and these are the generally notations that we use. If you go to Boolean algebra, that is a relevant subject to this logic that we are doing now, they call not as P bar, and as PQ, or as plus, exclusive, or as this, and C++, Java and all, you are aware of. Not is exclamation, and is like this, and OR is like this, and XOR is like this. That is how generally the notation do vary, but all of them mean the same thing that we discussed. All are binary or unary operators. After seeing what a preposition is, what a compound statement is, and how do we connect prepositions to get compound statements, and how do we evaluate the truth values of these compound statements, let us see a little bit about Boolean algebra. It's basically deals with bits and how you can talk about algebra of these bits. What is a bit? A bit is a binary digit, as we all know it, is a binary digit. It assumes either 0 or 1. If I am not mistaken, the bit might have come like BI and binary digit. So they have excluded one I and they may call it bit. It's only a guess. So bit is nothing but a binary digit which takes 0 or 1. Bits may be used to represent truth values, because we have been saying that a preposition takes a preposition will have its truth value as true or false. In fact, we can always say true is equivalent to 1 and false is equivalent to 0. So a preposition can take values like 1 and 0, which are nothing but bits. By convention, 0 represents false and 1 represents true. Boolean algebra is also like any algebra, wherein you got variables as bits and it has got some operators like natural numbers. What are the variables in natural numbers? Set of natural numbers, you get natural numbers. When you go to set of integers, you get what are the variables there on which you act upon or on which you operate upon. They are integers. Like in Boolean algebra, we have got variables like bits only, either 0 or 1. What are the operators that you can talk on them is plus and multiplication. Plus is exactly the same as we have defined OR. That means if given two prepositions and its truth values, we have defined the operator called OR. Because two prepositions can assume truth values, in fact two prepositions assume bit values either 0 or 1, you can also talk OR among these two bit values 0 or 1, 0 or 0, 1 or 0, 1 or 1. Okay. Plus in Boolean algebra is defined exactly the same way as we have defined OR in propositional logic. Because each preposition value is either true or false, you got one or true or false is nothing but 1 or 0, and OR is defined between them. So you can define plus in the same way as we have defined in propositional logic for given combination of truth values or for given combination of bit values. Multiplication is nothing but AND. That is how these two operators operate upon bits in Boolean algebra. And bit string is nothing but a length of ordered sequence of n bits. As you know, English string, when you say Delhi, this is a string of characters, isn't it? So you can talk of string of bits. This, for example, 1 0 1 1 1 0 1. This is a bit string. It is a string of bits. Okay. By convention, bits are written left to right. So we should know given English word, you know what is the first character and what is the last character. Similarly, we have to know what is the first bit and last bit of a bit string. Convention, we always say that first bit is leftmost and last bit is rightmost. For example, in this string, what is the first bit? 1 is the first bit, and traditionally some people call what is rightmost, what is second rightmost, and all these things. When rightmost is this and second rightmost is 1, that is how people call. But definitely first bit of a string always is the leftmost bit. And I think given a bit string, you know how to compute its value. That we all aware of that. I think when you traditionally do your programming languages, any basic programming language, there you will be taught how given a Boolean string, Boolean value, Boolean string, how do you compute its equivalent decimal value rather. One interesting thing about binary system is, if you realize, with the 5 fingers in each of your hands, you will be able to count 1023 numbers without use of any other external device. Thinking that each finger represents a bit, you make up a finger. If it is assuming 1, you make it down. When it is assuming 0, like that you get 1024 combinations, and that is how you can equivalently represent 1023 numbers using your 10 fingers. It's quite obvious, isn't it? To represent 0, you put all your fingers down, and to represent 1, you make only one finger up. You make one finger as the first finger and another finger as second finger, and you just come up with some representation how you want to do it. Probably you will be able to represent 1023 numbers with the 10 fingers that you have got. And how do you increment from one number to the other number? That we will see it. That's a very simple algorithm is there. Say all of us know that 0 will be represented in binary systems like this. If I am using 3 digits, you can represent as 3 zeros. Then to increment, if it is representing 0, how do you go to the next number? If this is the first, 0 is represented in binary system. If you got 3 bits, you represent all 3 zeros, then you get 0. 0 is represented like that. Then how do you go to the next number, that is 1? The algorithm is very simple. Algorithm states that you go to the rightmost bit, that is this, and flip it. What I mean by flip it, you just change its value. If it is 1, make it 0, and if it is 0, make it 1. Make it 1, 0, 0. 1 is represented like this. How do you go to the next number? The algorithm says that you go to the rightmost bit and you flip it, and in the flipping, when you are making a 1 as 0, then flip the next bit to the left. That means that we will see, to get 2 over here, what the algorithm is trying to tell us is, you flip this rightmost thing, but when I am flipping it, 1 is becoming 0. Whenever 1 is becoming 0, go to the next bit and make it and flip the next bit. What is the next bit? 0 is the next bit, so I will flip it. What I will get? 1. Because I am flipping from 0 I am going to 1, I can stop it here. So 2 is represented like this. We will see how we will get the other thing. Next, number 3, it is very simple. Go to the rightmost bit, flip it. When I am making 0 to 1, I can stop it, because while I am flipping, I am going to 0 to 1. I don't have to do anything. I can stop it here. If I am going from 1 to 0, I have to go to the next bit and flip it. Because I am going from 0 to 1, I stop it here. How 4 will be represented? I will go to this guy, and flip it. When I flip it, I am making 1 to 0. So I have to go to the next bit and flip that again. When I am flipping this next bit also, here also I am making 1 to 0. So I make it 0 and I go to the next bit. And here when I am flipping, I am making 0 to 1. So I can stop it here. So that is how I get. So that is how I can increment this bit strings nicely, and I can get to the next integer if I want. Okay, this is a simple algorithm that how you can increment your numbers, and if you got if you are dealing with binary number system. Okay, having seen that, if you have got two binary strings like this is a binary string. I think you have no problem in accepting is a binary string. This is a binary string because it is a string of zeros and ones. It's another binary string. Now you can probably talk of some operations on these two binary strings. The operators that you can talk is bitwise 0, bitwise and bitwise XOR. So this is simply defined like, you don't have to do anything. Taking 0 and 1, okay, suppose you are doing bitwise OR. Assume them as two prepositions assuming value 0 and 1, assuming false and true. How the OR operator there working in the similar way, you take the value and put it here. 1 and 0, when one preposition is taking truth, another preposition is taking false, whatever the value that OR operator is taking, put it here. When 1 and 1, when one preposition is taking truth value, another preposition is taking truth value, then what is the resultant will take? It of course takes 1. Okay, so assuming that these two are prepositions taking value as false and true, and what value the resultant will take if the operator is acting upon them is OR, you put that resultant value over here. Like that you can get the result. So bitwise OR is nothing but put the OR operations in these two strings, whatever the result that you get, you try to put it here and you do this. That is how bitwise OR, bitwise and bitwise XOR have been defined. Bitwise XOR is nothing but take 0 and 1, and when 0 and P and Q takes 0 and 1 values, then P exclusive or Q, what value it takes, that value you put it here. You go back to our truth table and see it and put that value over here, and that is how these operators have been defined. Go to each place and apply the bit OR operator on them and put the value here, then you get bitwise OR operator resultant value here when it is acting on these two strings. So we have learned what is a preposition and why it is important. We know given an English sentence how we can convert it into symbolic notations. You can call some of them as prepositions, and how English is connecting some simple statements to make a compound statement. Similarly, you can make it here. And given a compound statement in propositional logic with each preposition having some meaning in English, then we know what is the meaning of this compound statement. And we have learned about truth tables. Truth tables are very significant all these operators have been defined in a way, given a combination of values P and Q. Every operator is defined in a certain way, and we have seen what are the bits and bit strings, and next lecture probably we will cover proportional equivalences when two compound statements will be equal and how to make sure that the equivalence can be achieved by using some laws. Okay, thank you. Bye.